Thanks, guys. Thanks everybody for joining this seminar. This seminar is given by Dima Damen. She's a professor of computer science in the University of Bristol, and she's also a EPSRC Fellow right now. So Dima received her PhD from the University of Leeds, and also she has joined the Bristol University as a postdoctoral researcher, and then later on promoted to assistant professor, associate professor, and now she's a professor in Bristol University. Her research is obviously about computer vision, and she's particularly interested in object interaction, automatic understanding of object interactions, actions, activities, and so on. I think a lot of you know that Dima is a program chair for ICCV last year.
I'm now free again.
All right, maybe our paper is being allocated by you to the reviewers. And she's also an associate editor of IJCV, IEEE PAMI, and pattern recognition. So basically, almost all of the best journals in this field of studies. Now, she also is currently the supervisor of a group of PhD students, 9 PhD students, and 5 postdoc researchers. So really a very big, healthy team. So without further ado, I'll pass the table to Dima. And today she will talk with us about video understanding in an egocentric perspective. Thank you very much.
Great. Thanks for the invite. Right. I'm glad to be with you, telling you about our work on video understanding. It's a pity we can't yet be there in person, but fingers crossed that will happen at sometime soon. So what is video understanding? And I'll start by giving you an idea of what types of videos as a community we have been working with. And I will divide these by the perspective, what are we looking at from which perspective, as well as how much curation has been done on the video by the time we actually use it for, say, learning and inference. So the whole community started with movies. These are usually recorded, well thought of, good shots. There is a whole science about how to capture movies. They're well curated, well edited. And so most of the research was about understanding what's happening in movies. Interestingly, most of the interactions in movies tend to be social interactions, not object interactions, because that's considered boring from a movie's perspective. Then there was a trend of datasets that use sports, particularly sports captured using TV, again, very well curated. And then, of course, increasingly now we have these mobile recordings. They're a lot less curated, but they usually people capture what is happening in the scene, all the way up to all this current trend to live stream. So there's absolutely no curation. You're seeing the data exactly as is. Then there is a trend of using some of the footage that we all utilize on YouTube. These are how-to footage. How do I assemble a toy? How do I fix my bike? And this is actually introducing a different perspective, because you need to see how people are fixing, usually from a closer perspective, top view, or sometimes egocentric view, where egocentric view is from the perspective of the person doing the action. There are vlogs now, people capturing more and more of their lives. The type of footage that my group has been interested in for a while are a bit extreme in the sense they are egocentric and completely unscripted. So to an extent, they're closer to live streaming, but they are captured from the wearer's point of view. And if you haven't seen these types of footage, then just a quick glimpse on how we can capture long-term understanding of people's lives from these wearable cameras. Right, I hope this is not annoying to watch, but you can see why these bring interesting new questions, because they are fairly long-term. Right, so what can we see from this type of perspective? We really have a very good understanding of actions and objects. That's how they became really interesting as a source of understanding. There is interest also in understanding how people do it. Do they know what to do? What tools? Can they improve? How can we pass skills to them? And that's where assistive technologies comes to play. Then there is something, a few researchers are interested in, including ours, on goals. What is the person going to do next? Why are they carrying out that particular action? Then understanding of exact moments at which things take place. Then there is a trend of, can we now track and localize this person from the egocentric perspective? Perhaps the only thing the egocentric perspective doesn't cover is who, because you're always capturing the wearer, right? It's always from the perspective of the wearer. So you know who has done the action. You just need to do all that further analysis. And perhaps the big arch of our work is Epic Kitchens, which is a data set we've released first 2018 and then a second version in 2020. So what is Epic Kitchens? You've already seen some of these examples out of the footage I've shown you, which is we give people cameras, we ask them to go to their homes, and we ask them to record everything they've done in their kitchen for 3 days. During the recording, there's absolutely no instructions like capture this or don't capture this. But of course, when you capture these streaming, say, they're not streamed live, but I mean ongoing, not edited footage, you don't know how to give it a semantic meaning or what we call ground truth. And that ground truth is really important to train models, but also to assess models. So in this work, we kind of came up with an approach to do this efficiently. We're not a big group. So we did this via a set of live narration. So people would watch the video later and give us a description of what's happening, which really helped us to go and do effective, dense action segments without really wasting so much resource. And we released the first version, which is 55 hours of kitchen activities. We then went and collected further data, improved our pipeline. Basically, we now have, instead of an average of 13 actions a minute, 20 actions a minute. This is very, very dense, quick interactions in people's actual kitchens. Before our data set, most of the footage, almost all the data sets were in what we call smart kitchens, right? So you bring someone into a kitchen and you ask them to carry out a recipe. It's very, very unnatural because it's not your kitchen and you're really replicating a written recipe. Capturing stuff in people's actual kitchens was very transformative. And thus there was this line of work of Epic Kitchens. So as we said, people started recording as soon as they went into the kitchen, stopped recording as soon as they stepped out of the kitchen. And they gave us, after recording, these live narrations. So they basically describe using words how they what they're actually doing in those footage. And they do that in their native language because it's quite impossible to describe what you've done in your kitchen in a language that's not your native language. We don't know the names of most tools and components in another language, even if we spent X number of years in that foreign country. From these, what we call timestamps, we went and did what we call annotations, which is deciding exactly the start and end times, parsing those sentences into action classes and object classes, producing the current version that people use to train models. This is slowed down, but you can see the sentences written. They have a start and end time. They are overlapping at times. So you might start an action before finishing the other one. Very natural in daily interactions, though having been captured before in many data sets. But you can see the perspective as well as what type of footage we have and the density of these actions. Again, being naturally recorded, the data is very much long tail. The y-axis here is log scaled. So you have a lot more of certain actions than others. Again, very different than typical data sets collected to be mostly balanced. So this is a data set in terms of objects, and you can see we've kind of grouped them into what people use in the kitchens. We have 100 hours of footage collected in 48 different environments. I hope you could see, you could hear also the audio, but that's what we released. We released the videos, the frames, as well as the optical flow information of that data set. And currently we have a sequence of challenges that are close to what the community currently is doing. So action recognition is a standard problem that computer vision is attempting to solve. And in that, there is an assumption that you've already localized the action. So you know the start and end of an action. And your only objective is to say what the action, what the verb and what the noun is. So from all that wealth, action recognition, despite being the most common problem in computer vision, has lots of assumptions that you know the start and end and only one action is ongoing within those boundaries. But from this action recognition challenge, we have a leaderboard and people submit. This will be the 4th year we have the action recognition challenge. The challenges are now open. We have 5 of them: recognition, detection, anticipation, domain adaptation for recognition, which I'll tell you a little bit about, and retrieval. And this is from our last virtual gathering, a set of winners from last year's challenge. If you want to know more, go and have a look. The current challenges are open until the 1st of June. So this is basically the premise of the data that we're using. And now what do we do in terms of research? So perhaps the first thing that was initiated or triggered by the way we collected the data set is whether we needed to do the expensive task of going and localizing those start and end times of actions. Could we learn from these narrations? And there is similar trend of doing so from narrations of YouTube videos. However, they're never as dense as this, right? YouTube narrations tend to be a lot slower. They tend to be like a few sentences a minute as opposed to 20 sentences a minute. So that was the first question. Can we learn from what we call single timestamps? And how can we change the approach of computer vision to do that? So in this work, we kind of said, okay, these are rough estimations of where the actions are. So we know the action exists somewhere close, and we needed to refine those actions in location and duration, while still knowing that we have a certain order and that it's roughly around that action. So that means we start with these single timestamps with a certain proposal of where we think the action is. We train a model, and from the responses of that model, we can refine the location of that action. That's basically with changing what's called the ground truth or the labeling. We're fixing the labeling or rectifying it towards at the end, localizing from the bunch of sequences the exact start and end time, which we use to train a model. Of course, in testing, we're testing with still the basic ground truth agreed by a human so that we can compare this way of learning to standard learning approaches. But I very much like some of these visualizations that Davide, the student who did this, he's now a postdoc at Edinburgh, did with this work. So basically you can see that initially the actions are kind of long, and then you get the exact moment the person is opening a drawer or moving a cup. Interestingly, these discovered boundaries tend to be even tighter than the boundaries we have been using in standard computer vision. So they're actually finding the most discriminative part of the action. Right. So in this talk, I'm planning to do an overwhelming aspect of different topics rather than focusing on one paper specifically. I'm hoping that by having this map, we will keep track of the different topics that I will tell you about. These are all fairly recent works that we've done as a group, of course, along with lots of collaborators, and they're divided into 4 topics. How well you're doing something, what level of supervision you're using, multimodality, particularly vision and language, and vision and audio. I will present the first. I'm not going to talk about all these, but these are the subsections. I'll present at least one work from each section, and I will pose for questions after each one because I know people tend to forget about the questions. So I'll present the first part on skill determination, and then we can discuss questions up till now. So what is skill determination? This is a line of work that was carried out by Hazel, currently a postdoc at Amsterdam. And basically the question is, what can you know as a human observer when observing 2 people performing the same task? In this case, it's a drawing task. It's captured using both a static camera and an egocentric camera, which you can see now showing in the corner, right? So we analyzed both the static and the egocentric. But what can you understand? And it's very easy to give this to 2 humans and to ask them to say who is performing a better drawing, right? It's actually quite impossible for them to agree why they think this person is doing better. They will tell you it's the expression, it's the strokes, they will kind of pick a different explanation, but they will all agree that certainly the person on the right is exhibiting a higher level of skill. So you were wondering, out of some labels for a variety of daily tasks, whether we can have a model that can also predict whether someone is doing better. And in this case, we're having 3rd-person video. So we're observing people from YouTube, braiding hair, and we have labeled those. So we know that the person at the top is exhibiting a higher level of skill of this task than the person at the bottom. Yeah, so in this work, what we do is we look through the video, we extract an understanding of the motion, of the action, of the objects. So these are the typical backbones, we call them. Then you can combine these across time, and you can train a network to basically predict, give a higher score for the one on the top than the bottom, right? And the whole thing is refined. So in some sense, you're changing what the network needs to learn in a way that ensures it can match your human predictions. When we did this, so purely putting something in and getting something out, the first conclusion was, okay, we are making this assumption that all aspects of the video are relevant to skill. When we do action recognition, yeah, you have an understanding out of what the action is from the whole video. But when you focus on skill, there are many steps in braiding hair, like combing hair, which doesn't really reflect skill. There are particular aspects that are skill relevant. And in computer vision, we tend to try to learn these from data as opposed to impose it by a human understanding via what we call an attention model. You can think of it as a weighting aspect. So instead of basically saying, accumulate all the evidence from the video, learn how informative each part of the video is to decide on the skill level. And one thing we did in this paper is that showing by training this to outperform uniform, it's actually a more stable learning than just learning an attention module. By doing this, we were actually performing fairly okay on the test set. But interestingly, it was not picking up mistakes as evidences of low skill. So basically mistakes in a video were not really being given much attention, which was very confusing to us because, to us, it's the main evidence of someone exhibiting a lower skill. And that's the nature of these models being trained, is the nature of these shared weights, where you actually tell people to pick the common as well as the distinctive. And in this work, we've proposed to actually have multiple attention modules that specialize using a particular loss that expects one to attend to what we call the pros, so what's actually distinctive of high attention, and the cons. So we have multiple attention modules. Without the additional loss, they will learn exactly the same. With this loss, they will try to specialize into high skill level and low skill level. Perhaps this becomes evident when we look at the output. So these are the parts of the video that were picked with high attention as evidence of low skill. We can see, for example, in the case of the origami, it is picking up people unfolding, right? So it's frequently saying this is a particular behavior that is related to people showing low skill. And in the middle row, on applying an eyeliner, you see that all these people are removing bits of the eyeliner. And that's again being picked up automatically by the model as evidence of low skill. And similarly, you have the other end, which is the high skill. So you see in the origami, people firming folds, and this is being picked up by the model as evidence of high skill. And I'd like to start with this work because it really showcases to people outside computer vision what machine learning had done for computer vision, because it really had transformed the field. Before that, we used to kind of think a lot about what the human will understand and enforce that understanding to the machine. And currently, it's a lot of data-driven approach. The bottom line shows people hesitating and thinking. And the system had shown that in drawing, hesitating and thinking is evidence of high skill, while in makeup, hesitating and thinking is evidence of low skill. And this is not something we could have even envisaged as humans, and this can be learned from data. Of course, you end up being biased by the data you learned, you trained the model from, but critically, you tend to pick on these understandings that might not even have occurred to humans, but they make sense when you explain them. Any of the papers I'll talk about today, if you want to know more code, data, paper, you can refer to the relevant web pages. But before I move into supervision, I think it's reasonable to pause for a few minutes for urgent questions. Questions, concerns?
I do have a question, if possible. In your previous slides, you obviously show some of the temporal attention results, and it's very good that they are short duration of clips, which is very easy for humans to understand. But I would also think for the best performance of the network, from the network perspective, perhaps the temporal attention will be a bit more sparse. So you have individual frames that are sampled. Yeah. So how do you balance the attention for the network and attention for human interpretation?
The attention is spatiotemporal. If you look at the paper, you'll see the spatial attention. I find that the temporal a lot more easier to understand. The spatial tend to sometimes pick on certain tools that the people are using or the locations of the hands, but they're always difficult to understand. You can argue against or with them, but the model actually is learning spatial and temporal attentions. Okay, so No worries. I'll tell you about another line of work, which is what level of supervision you can use in training these models. And that's a big question, both computer vision, machine learning. Can we learn with less supervision? And one aspect we have that naturally comes with Epic Kitchens, the data set I told you about, is really recording in multiple environments. If you actually take these videos and optical flow, so the motion, the RGB and the motion, and you train a classifier, this maybe not in the last year, but a couple of years ago was the standard for learning, which is you have a network that looks at the appearance and a network that looks at the motion, and you combine their information to do a classification. But if you train on one environment and you try to test on another environment, the system tends to really not generalize well. In fact, if you look at the observations where blue is what you've trained on, red is what you try to predict on, those feature spaces don't even align in a nice way to even do anything meaningful. The current trend to do unsupervised domain adaptation assumes you have access to data in the new environment, but without labels. So you have access to what we call the target environment. You can collect data, and you can use that to train the model, but you don't need to collect additional labels. And in this work, which was presented in CVPR 2020, what we did is that we kind of added some interesting multimodal losses to allow these things to align without additional labels. Because in video, we have this motion and appearance. What we did is that we passed information from the first and the second environment into a loss function that solely predicts whether data comes from the same action or from different actions. So this is purely a classifier that says same or different. And just by adding this self-supervision, which we can do in the new environment, because time or alignment of time naturally comes with the data, doesn't need additional labels. That's what we currently call self-supervision. So the data that is the knowledge that's available in the data without additional annotations. You can see that the data tends to cluster nicely. So what was messy here, just purely by doing the self-supervised task, becomes nicely clustered into action-relevant clusters. And then on top of that, you do the typical alignment, which has been done by many ways, perhaps more commonly by what's called as the adversarial loss and the gradient reversal layer, where you say, I no longer want to be able to distinguish whether the data comes from kitchen 1 or kitchen 2. You basically remove that knowledge out of the training data, and you do that for both streams. Adding these combinations allows you then to localize and be able to look at the example of cutting from one kitchen and basically say the person is cutting without having seen that background and those objects and that person. So if you look initially, before we do the domain adaptation alignment, these two videos are very far. There is no hope that you can localize. Once you do the self-supervision, they get closer, but they haven't yet fully aligned. And by combining the self-supervision with the adversarial, you not only align them, but you can actually recognize. And in fact, this is currently now one of our challenges. And this has triggered new and interesting research into video understanding through unsupervised domain adaptation, a topic that has been solely done in images before this work. There is a new paper on arXiv I'm not going to talk about, but we attempt to do the same for retrieval, where retrieval is the task of aligning videos and captions. Again, we assume we have videos and captions in one environment, videos without captions in the other environment. That's not a paper I will discuss. Now I will move into another question we have in supervision, which is, can we learn from few examples? Can we, from just 2 examples of a cutting action, be able to recognize that? And as you know, current machine learning approaches are very data hungry. So if you actually tell anyone currently that you can learn from 2 examples, you know, the notion is that's never going to work. But there is increasingly interest and new methods that aim to learn from 2-shot recognition, from 2-shot, 3-shot, 5-shot recognition, but they have to do it kind of completely differently. The current set of trends is using what we call a support set. That means you always have access. You don't train a model that learns all the classes. You always have access to those examples, whether it's walking, running, cutting, and then using that support set, you want to think about this query and align it to the best class. So there are lots of assumptions still in few-shot learning, but within what's agreed as few-shot learning, So that one of the assumptions is, you know that this query is out of those classes. That's a big assumption. But taking that assumption as the current agreed problem as few-shot recognition, what can we do? So again, this X-shot assumes that there is a support set, and the aim is to learn a classifier using the support set to classify the query. Basically, all prior work prior to the paper that I'm going to tell you about, which was presented last CVPR, assumes that you take every query and every video separately. And in this work, inspired by similar trends in images, so this is a cross transformer that was presented a couple of years by DeepMind. They basically say you can't really expect that all parts of the query is present in one image. So you basically want to accumulate evidence from multiple images in the support set. So inspired by that, we want to do the same in videos. But in videos, you really can't really recognize actions from a single image. An action is usually at least 2 images. And in that, we use one of those representations common in computer vision, which is instead representing an action as 2 frames, ordered frames, 3 frames, 4 frames, right? You sample a combination of frames, and these are called pairs, triplets, etc., representations from the video. So that's the premise. Let me tell you about the paper, which we call Temporal Relational Cross Transformers, or TRX. So we have the query video, and we have those classes, each with a number of videos as their support set. And what we aim to do is to extract these pair representations. So, frame 1 and frame 3 from both the query and the support sets. And if we do that for all possible pairs in the support set, we're basically doing a typical transformer attention, which is you map your input and you kind of learn that mapping to understand the similarity between your query and what you have, which is the support set. But doing that from a single pair might not be reliable. You might want to do it from multiple pairs. Sorry, I'm shifted the order. So this is the initial thing. You actually produce an output of your attention and you compare that to your query, and you know whether you're closer to class 1 or class 2. And as I said, from a single pair might not be enough. So TRX is actually all possible pairs from queries and support sets. However, this is really not expensive. What's expensive is what we call the backbone, which is extracting features from the actual frames. This is only 10% of the memory and the time constraint of the method. So it looks expensive, but not as expensive as it looks. One other thing is that you might not really be able to learn a good action representation from pairs. So you can do the same in triplets. And in fact, we do combinations of paired triplets and quadruples and compare that and analyze it in the paper. And you can average those representations from pairs, triplets, etc. This paper is really doing impressive performance on all current. Again, I told you that the benchmarks are a bit funny. They're 5-way, 5-shot. That means you have 5 examples of 5 classes. And these are the different data sets, and sometimes you have multiple splits from multiple papers. But the paper did quite a big jump over what was before that the state of the art. Toby, who did this work, has also reproduced good code for all of these methods. So that's a good contribution. In terms of, if you want to actually take this further, you can have 1 bit of code that can compare all previous methods as well as ours. Critically, what we want to show is as the number of examples increases, TRX outperforms the previous work by a bigger margin, because the whole trick is about learning from multiple examples in the support set jointly. So as the number of shots or examples per class increases, you can see this bigger margin that TRX performs over prior art. And as I said, there is a great GitHub that Toby has created for TRX. Right. A third bit of work on supervision is a paper called UnweaveNet, still not published, so it's available on archive. It's the first time probably I'm presenting this, so this might be more difficult to explain. You refine your explanation with time. But I really like the idea, and I hope to share with you the notion of what UnweaveNet is about. So I told you Epic Kitchens has really done this idea of just collecting long-term footage. If you look at one person going into the kitchen in the morning and you try to understand what they do, they really jump between different goals or activities. So you might go there, start boiling the kettle or put the coffee to brew, cut the bread, put them in the toaster, realize you have a bit of waiting time, go and maybe do the dishes or put stuff away. And you keep going back and forth between a number of activities. And prior work acknowledged that this happened, but never intended to link those activities, particularly the notion that you resume something after a break. It's not a new making coffee. This is the same making coffee that you paused and you're going to resume after having started another thread. This idea of looking at these, what we call threads of activities, and thus the name of the paper UnweaveNet, similar to basically maybe understanding storylines in movies. And there had been a thread of works in that way, but nothing on daily activities, maybe because of the lack of data sets with that in mind. Having had epic kitchens with this natural collection, it was very evident to see that there is this notion of understanding what the person is doing as they do it. So UnweaveNet, as we think it is a new understanding of how we can parse or understand videos. Perhaps parsing is triggered by the way we want to understand videos. So basically you say, okay, I'm starting the video with no memory, which we call the thread bank. As I go through, I'm accumulating an understanding of what the person is doing. So I know they're doing activity blue. And then over time, I realize maybe they started something else. So I start another thread in the thread bank. And at some point, I want to kind of say, okay, I'm now resuming thread 1 until a certain point in time where I might be starting a new thread, etc. So this notion of parsing the video and coming up with a final explanation of the whole video is what UnweaveNet is about. It's a new problem currently in computer vision. Might seem intuitive, but I don't think we've looked at it. We've looked at videos in this way before. So this is a slide that Will has prepared. He calls it video through the eye of UnweaveNet. So what you'll see is this explanation of whether this is in which thread it is, what's the probability of this being a new thread, the current clip number, the prediction of which thread this belongs to. I think this is the ground truth. And then what you see is you see clips coming, and then you see kind of notion that now I believe the person, I'll go back, hopefully that will be able to, now the person is actually, the probability that the person is continuing the blue thread is low. And so there is a higher probability that this is a shift to a new thread, which we're calling the new thread now, as the person is doing something new. Right, so this is the start. And the people are now moving into a new activity. And they're staying in that activity for a while, according to the UnweaveNet understanding. So these are predictions, probabilities of which thread you belong to. And at some point, you might realize, okay, I think the person had again switched to something new because they're clearing up or something. Okay, so with that intuition, I'm hoping that the idea is clear, which is trying to parse what the person is doing. What can we do? What is this module that will be able to replicate this idea of parsing? So currently what we need is an understanding of the memory, which we call ZT, the input clip, the current observation. And then we have two modules. One is a controller that decides what happens to the current clip. And one is a memory update or a thread bank update. And that's the overview of UnweaveNet. The controller is a transformer. So it's an attention module that takes the thread bank, that takes a token for whether this is a new clip. So everything is learned. And that takes the current clip and tries to learn to predict this representation. So the clip representation, the thread representation, the transformer, and the new token is learned from data. And the outcome are those predictions of which one we believe, which thread we believe this clip belongs to, or is it a new thread? This is the controller. And then the thread bank is purely a bank that says, now, given that decision, I believe this belongs to this thread, you update that relevant thread. Hoping the notion is intuitive. The whole thing needs to be trained end to end. So the backbone to say what features we want to extract from these clips has to be learned, because we really don't know what is the meaning of an activity or a thread. But these are ongoing things. So inspired by language models, we are training them in a supervised manner using teacher forcing. That means at every point in time, we've populated everything in the past using ground truth, and we only train for the current step. But we do that for all steps. And the loss is then imposed on this output prediction PT to be actually matching the ground truth. Right. How do you even train this? We don't want to go and label all our footage by people shifting between activities. We might need some label data, but we thought we could utilize self-supervision, which is this idea that there is enough information in data to actually inform the base training of UnweaveNet. So we synthesized, we basically invented stories out of videos. We took videos, we took different clips. So we said, okay, this is the first activity, this is the second, the third. We randomly sample number of threads, number of clips per thread, and we formed this synthetic storyline. So that means we broke this 2 consecutive clips into 2, and we are expecting the model to learn that this is a continuation of this one. This is the synthetic pre-training, which is really good because it allows us to train most of the parameters in the model. We then have a small scale set of labeled sequences, which we ask people to go and say, when do you think the person has shifted their attention to another activity? And that is, in training perspective, considered small, out of Epic Kitchens. As you can see, most people are still doing 1 activity, 2 activities or less, 3 activities of less, but we have examples of people shifting. And this is the typical outcome. So you have the model's prediction and the ground truth, clip index, prediction, ground truth, the decision scores. And this is an example of the model saying, I believe the person is continuing the same activity. And in the bottom line, you see that even with large motion, the person had the system had learned that this is still continuing the same activity. I think I haven't put lots of examples of people shifting between activities. I need to refine those slides to give you more examples. But please look at the paper and the accompanying video to see we actually have people shifting to activities and resuming. And I think if you have time, I can pick those slides for you. Right. So until now, I have given you an overview of these sets of works where we try to learn with different levels of supervision, either with some training data that is unlabeled, unsupervised adaptation, few shot, or even thinking about videos in a completely different perspective with self-supervision as the main pre-training for these activities. For telling you about multimodality, vision and language and vision and audio, I think supervision, or this bit, is the hardest in terms of the most different to what others are trying to do. So I can pause for quick questions. If not,
so can I have a question?
Absolutely, yes.
So thank you for presenting me very interesting research about UnweaveNet. And I'm curious about how many, are there any problems with, such as overcutting problems? I mean that, if you use them, if the video
Over-segmentation. Yeah.
Yes, it's true.
Yeah,
so are there any problems kind of that?
There are problems of over-segmentation. Of course, what we had to show in the paper is that we outperform other approaches, which might be more naive in that sense. So they over-segment even more. There are 2 main points of failure in UnweaveNet. Over-segmentation is certainly one of them, particularly if the person is returning to the activity from a very different point of view, where the system just doesn't have enough evidence to say this is a resuming. And the other aspect of UnweaveNet is a delayed start of the activity. So usually we don't get the exact moment in time at which people believe you've shifted. Sometimes we need a bit, 1 or more clips before we actually realize which thread it is. And of course, that means, do we need to do this online? Can we have a bit of buffer and fix some of the errors? But we haven't worked in that. Currently, we're taking decisions in a greedy manner. We can't go back and refine them. But yeah, the two modes of failure are over-segmentation and delayed prediction of the thread.
Okay, thank you.
Welcome. Okay, let me tell you a little bit about vision and language. And again, as you can see, most of the ideas are out of the data set we've collected. So basically what we have is we have sentences that people have given. So we can divide what we have into a video and a text. And retrieval is this task of either taking a video and ranking all the texts you have in a gallery where you would like your correct text to be as high as possible. So this is the retrieval task, as opposed to the recognition task where you know a set of labels and you have to retrieve, you basically classify. And the fun thing about cross-modal retrieval is you can always evaluate the basically both modalities, video to text versus text to video. So in this first line of work that was led by Michael, he's about to start his lecture at Bristol, but this was the line of work at the end of his PhD, where you have the sentence and the video. And his main premise is to parse the video into its different parts of speech. The objective in that is actually to learn what putting means regardless of the action, and to learn the object regardless of the object, and to learn the object regardless of the action. And that allows you to generalize to what we call zero-shot learning, so putting something new or doing a different action with the DOE. So he's basically separated the embedding space or this retrieval space based on the part of speech. So you have a verb space and a noun space. You can still combine these two spaces once you've specialized or you've had this particular view. You can still do the typical retrieval, but only via these part of speech embeddings. So this is the input. You have exactly the same representation of the video, but now is projected differently, whether it was in the noun space or in the verb space. So this is the verb space, the noun space. They have their own individual losses, and they're combined again to have a final losses into this joint space. I really like some of the visual outcomes of this, which is you now have in this noun space, you've grouped all these videos of the chopping board, regardless of what you're doing with the chopping board. So you're focusing on nouns. And interestingly, if you look at the verb embedding space, you see that it had grouped open and close of various object actions. And by understanding what really open and close is, you can generalize to unseen activities. So this is how actually we started to look at parts of speech. And we've taken this step further to look at adverbs, which again are related to how people do things. We don't have long sentences in EPIC, so we could not do that on EPIC, but we can do that on How to 100 Million, which is a large data set out of YouTube videos. So people typically describe particular actions using adverbs because you need to do them in a particular way. Turn this slowly or fill it partially, right? If you don't satisfy that adverb, you probably are doing that particular step incorrectly. So in this work, we assume that we parse the sentences, knowing the verb, which we call the action, and the adverb, which we call the modifier. And this is inspired by terminology in objects and adjectives. So basically, we're saying it's a rolling action, but it has been modified by that adverb. So it is rolling quickly. And we have the video. And what we aim is to embed the video, not only close to that action, but close to the modified version of that action, which is a projection in that, a transformation in that space. So basically, we want to share that modifier, which is quickly, between different actions. But we want to learn the embedding and the modifier in a way that eventually we can then understand something else quickly, turning quickly, or opening quickly. And life would have been easy if we really had good alignment between this text and the video, but we don't in YouTube. You don't exactly know where in the video you're rolling. And for that, we use the typical attention mechanism. So that means we say, okay, we're looking for a rolling action. Can we put that action into our attention query saying, find rolling? Then you actually learn this attention, learn the attention module. So you learn to attend to rolling, look for where it is in the video, and embed that video close to the modified action. And again, I really like some of the visuals that come out of this work. So you're going to see the border thickness implying when the system believes they're attending to the action mix. So they know it's mixing, and the system is attending to where mixing happens and predicting the adverb. So once it knows mixing has taken place, it needs now to predict out of 6 possible adverbs. So it knows this is quickly, it can predict to mixing slowly, rolling quickly or rolling slowly, turning quickly and turning slowly. And again, it needs to look within the video when the person is exactly turning, and then to be able to predict the adverb. The last bit of, maybe I'll skip the semantic similarity. I don't know how we're doing with time. I'll skip the bit on semantic similarity and go into audiovisual. I've kind of given you an idea of what type of vision and language problems we're interested in. Because I think it's important to talk about audiovisual and where audio really helps. I've already told you EPIC has audio, and I think this is one of the pioneering works we've done, because if you can, look at this video and try to understand when the person is actually blending, that's really hard. But if you hear the audio, and apologies for the noise, your understanding of the start and end time changes dramatically, including an understanding of how you do something. So if you see someone smashing garlic, you might not know how much force they're exerting. But if you see the same video with audio, your understanding of how much force they're putting is different. So there is a lot of knowledge in audio. And in this work, which was presented in ICCV this year, we really focused on just audio only input. What can we learn from the audio? And we've recognized that there are 2 types of sounds of actions. One is what we call harmonic sounds. And the other is what we call percussive sounds. Hopefully the intuition is obvious. And the same thing exists even in other datasets that are not egocentric. So there is a VGG sound dataset from Oxford. And again, they also have different actions outdoors, not only egocentric. And you can divide the sounds into harmonic and percussive. So in this work, which we call auditory slow fast, we kind of said that we're inspired by the evidence in neuroscience about this ventral dorsal stream in the auditory system. There's prior work of how to use this in visual, but actually also exists in the auditory system, where the ventral stream has high spectral resolution, the dorsal has high temporal resolution, allowing them to then attend to this distinctive aspect of frequency versus temporal localization. And again, as I said, there is evidence of doing this slow fast in video recognition. So very much we're following the same trend. So this is the auditory slow fast, where we have the same audio represented in different ways. One by focusing more on the frequencies, and one by focusing more on the temporal information. So the number of channels versus the temporal representation is different in these 2 different pathways. The slow pathway has a low temporal precision, but a large number of channels. The fast has few channels, but high temporal resolution. One feeds into the other through some lateral connections between these pathways. And we also have separable convolutions, because the spectrogram, the way you represent audio, one dimension is time, the other dimension is frequency. It's not like images where the 2 dimensions are homogeneous. So we have separable convolutions. Again, has been tried before in audio, but not within this setup. And the outcome is really interesting. We outperform audio-only approaches on VGG sound and EPIC. And very recently, and we really showcased that the slow stream is attending to sounds that are more harmonic, like cat hissing or zebra or thunder, etc., while the fast stream is attending to these percussive sounds like playing tennis, clapping, etc. So the motivation matched the outcome. And very recently from DeepMind, they kind of built on this work by acknowledging that this slow fast architecture is good at learning rich representations from audio, even in other types of domains. So they've tested this on speech, music, etc. That wasn't our initial motivation, but they showcased that the same architecture is really useful for different domains. And this is part of their paper, which they showcased already that the slow fast architecture is kind of very strong. And again with their improved, so that's on speech, music, and on audio set. Vangelis, who's just submitted his thesis, has prepared really nice code and pre-trained models on VGG Sound and Epic for those who are interested. Right, and in the remaining 8 minutes, I'm going to take every minute that you're giving me. I'll tell you about some explainable work that we're doing, which is given a video, if you want to predict the action, we know that the whole video contributed to the outcome of the action. But in this work, we want to know exactly the attribution or the contribution of every frame in the video. So this is an explainable approach. That means we know the outcome of the model. We just want to know where that outcome comes from. Okay, I'm going to skip some of this just to show you some of the results. Okay. So basically, we give a value per frame on how much that frame is contributing to the decision of a class. So this is the class of pouring, and we can showcase exactly which frames are making the most of the evidence of pouring. Now we can take examples. This is exactly the frame that makes the model decide it's this particular class. And we show that for Epic, where we show that predicting the action and predicting the object doesn't occur at the same place in the video. So knowing that someone is opening happens at a certain point, but knowing that they're opening a drawer happens at another point in time. And that's really interesting because we kind of always think of these actions as one thing, but really the act and the object on which you act on are discriminative at different locations in the video. Last but not least, leaving 5 minutes to breathe, is do we have enough data to do egocentric vision? And Epic Kitchen was large scale when it came. I am pleased to let you know, if you haven't heard of that, that Ego4D, which is this large scale data set collected by 13 universities, including Bristol, is now out there. This is the type of activities we've managed to capture. The data is huge. A paper has been out, 83 different authors or 84 different authors out of all the different universities, also in partnership with Meta AI. And you can visit the webpage, Ego4D data. You can even see some of the footage collected around the world, in India, in Africa, in Latin America, in the US, in Europe, and in East Asia. And the data has been narrated in exactly similar ways to what I've told you about Epic. So people actually, you have a sentence describing what the person is doing. So you also have these videos along with those descriptions of what the person is doing. The data set is, I don't know whether I mentioned this, did I? Yeah, it's 3,670 hours. So yeah, I don't know how much we will be able to explore out of this data set in the next few years, but it's collected at 74 different cities and 9 countries. So if you want to do egocentric, this is the best time. There is sufficient data, a large consortium, and 5 challenges in predicting the past, memory, hand-object interaction, diarization, social, and forecasting. With that, I hope I haven't given you much headache. I hope that I've shown you that video understanding goals really depend on the video source. Egocentric really offers this unscripted footage with plenty of potential. Audio and language cannot be underestimated as both input and labels. I haven't told you much about frame attribution methods, but they really offer insights into what we can do next. We've had Epic Kitchens now for a couple of years. We have Ego4D, which people just started downloading this week. It's massive scale and there's plenty of potential. We need everybody who's interested because I don't think we can do this on our own. And I get the privilege to come and present this, but this is really hard work of brilliant set of PhD students and postdocs that I get the pleasure to present to you. Thank you very much.
Thank you very much. Any questions from the audience? Any questions? Well, I think there's one thing I just wish to mention. The explainable part at the end, even though it's very short, I think it's very, very interesting to us, especially because in our team, we are doing some sort of surgery video analysis. They're sort of egocentric, but you're using micro cameras, and then you have the tools working around, and the explainability is crucial when you try to explain, when you try to make decision on why this is such a decision, why this is the start of a surgery or not, especially to these healthcare professionals. So that part is going to be very useful.
Yeah, hello. Hi. Yep. I have a curiosity about the unsupervised domain adaptation. In fact, I'm doing a similar project on adapting a pre-trained model on 3D mesh. So I just wondering, do you think whether it is possible to, for example, your data set is the videos from the real world. Yeah, correct. If some styles are added to the video, could we do a similar domain adaptation?
Some styles?
Yeah.
What do you mean by some styles?
For example, if some video games can also produce similar videos, they can cook, or they can yeah.
You mean synthetic? Yeah, I think I always tell them when people tell me about synthetic footage, until someone gives me a synthesizer that can cut a tomato or a cucumber, because there is nothing out there. There's absolutely nothing in the synthetic domain that can do any of the kitchen activities with even with badly, right? So if you look at some of the brilliant approaches of virtual homes, etc., they stop short of actually doing any interactions. So the person walks to a fridge, the fridge magically opens, right? None of the current simulators can do any interactions. Maybe they can now open cupboards, but as I said, once they cut a cucumber, I would be interested.
So I think the domain adaptation mainly solves the lack of annotation problems. Yeah.
You would hope, yes. It would be amazing if there is something synthetic input, but all the current synthetic, I think it's all gaming driven, right? I don't think if there was an interest in people cutting cucumbers in games, I'm sure people who are doing gaming would have sold them. But currently there is no interest, and that's what we need. That's the type of interactions that we actually need to learn from. So, and it needs to be natural in a way that we can learn from it.
Yes.
What bridged the problem in driving between synthetic is because the driving simulators are now very natural. But the number of domains for which synthetic is natural is very, very limited.
Yeah. Okay. Thank you.
All right, if there's no more questions, shall we call it a day? Thank you very much, Dima, for coming and talking with us, and we appreciate your talk.
Thanks for the invite.
We have a chance to talk more in the future.
Thank you.
Thank you, guys. Thank you very much.
Sure.
Thank you.